You know when you look at a snowflake, really look at it, have you ever wondered how something that looks so perfect, so purely geometric, actually works in the real world? Well, it turns out there's this incredible hidden connection between its beautiful abstract shape and the very real physics of heat.
So, let's take a famous example, the von Koch snowflake. Mathematically, this thing is just wild. It has an infinite perimeter crammed into a finite space. We can describe its shape perfectly with math. But what happens when we pull it out of that pure math world? What if it were real? And what if it were hot? How on earth would an object with an infinitely complex edge even begin to cool down?
For the longest time, nobody even thought of this as one single question. You had mathematicians over in one corner talking about the fractal static intricate shape, and then way over in another corner, you had physicists trying to model the dynamic flow of heat. They were looking at the exact same object, but for all practical purposes, speaking completely different languages.
And I'm not just talking about a slight difference in dialect here. We're talking about two fundamentally different ways of seeing the world.
Think of it like this. On one side, you have the language of geometry. It's the blueprint, right? It describes the fixed patterns, all the wiggles, the beautiful self-similarity. On the other side, you've got the language of physics. That's all about the action, the temperature, the energy, how it all flows and changes. One is a snapshot, the other is the movie.
So, this massive divide leads to a really huge question. Is there some kind of fundamental link? Could the numbers that define the fractal shape, you could call it its geometric DNA, could those same numbers also predict how it behaves physically? In other words, is a fractal's geometry its destiny?
Well, it turns out the answer is yes, and the key to bridging that gap was found by listening for a kind of hidden rhythm, something baked right into the fractal's very structure. This idea is called complex dimensions, and honestly, the easiest way to think about it is that every fractal has its own unique song, a specific rhythm that comes from its geometry. Complex dimensions are just the individual notes, the specific frequencies that make up that song.
Okay, so if it has a song, how do you actually hear the notes? Well, mathematicians came up with this amazing tool that kind of acts like a prism for fractals. It's called a scaling zeta function. You feed it the basic rules of how the fractal is built, how it scales and repeats, and this function breaks all that complexity down into its pure fundamental frequencies. And those are the complex dimensions.
And for decades, this is what everyone figured they were for. They were this brilliant tool for geometry, perfect for describing all the intricate patterns in a fractal. But the story was supposed to end there, just in the abstract world of pure math.
But then, a recent breakthrough showed that these dimensions speak more than just the language of geometry. It turns out they're fluent in physics, too.
This is the moment it all just clicked into place. Researchers Hoffer and Lapidus discovered that the exact same numbers, the complex dimensions that describe the shape, also perfectly describe how the fractal's heat fades away over time. The notes from the fractal's shape were also the notes of its physical song.
This discovery completely changed the game. It turned complex dimensions into a kind of scientific Rosetta Stone. All of a sudden, we had a universal language that could translate the geometric blueprint of a fractal directly into the story of its physical life.
So, how did they pull this off? It was a really clever three-step process. First, they just started with the standard physics equations for how heat flows. Second, and this was the genius part, they built a new equation that specifically included the fractal's unique self-repeating pattern. And third, when they solved that new equation, the answer wasn't just some random number. The solution was the fractal's own complex dimensions, popping up right there in the physics.
So what does this all mean, now that we have this universal language? The implications here are actually pretty profound.
It means that for these fractals, geometry really does become destiny. That static shape you see on paper isn't just sitting there. It is actively, physically dictating how things happen on it over time. And if you want to see the proof, well, this table is the smoking gun. On top, you've got a formula that's pure geometry. It basically describes how much space the fractal takes up. On the bottom, you've got a formula for how its heat changes. That's pure physics. They look a little similar, but look closer at what's in control. In both cases, the key variable driving the whole thing is omega, the complex dimensions. The exact same musical notes are conducting both the shape and the physics.
So why is this such a big deal? Well, for one, it builds this beautiful bridge between the abstract world of math and concrete physical reality. It means we can now look at the pure geometry of a complex object and actually predict how it will behave physically. It proves that shape isn't passive. The tiny details of a fractal directly control how it loses heat, and that's a principle that could apply to all sorts of things, in nature and in engineering.
It really makes you wonder, doesn't it? If a fractal's geometry is a language that dictates its heat flow, what other universal languages could be hidden in the patterns all around us, just waiting for us to find the right key to translate them?